Hello.
Hello. Yeah, I really thought it could do that. And
Okay. Uh, I don't know. Can you go first?
okay, multi-layer perceptrons. In this chapter, we will introduce your first truly deep network. The simplest deep networks are called multi-layer perceptrons, and they consist of multiple layers of neurons, each fully connected to those in the layer below, from which they receive input, and those above, which they in turn influence. When we train high capacity models, we run the risk of overfitting. Thus, we will need to provide your first rigorous introduction to the notions of overfitting, underfitting, and model selection. To help you combat these problems, we will introduce regularization techniques such as weight decay and dropout. We will also discuss issues relating to numerical stability and parameter initialization that are key to successfully training deep networks. Throughout, we aim to give you a firm grasp not just on the concepts but also of the practice of using deep networks. At the end of this chapter, we apply what we have introduced so far to a real case house prediction. We punt matters relating to the computational performance, scalability, and efficiency of our models to subsequent chapters.
Okay, so punt is like a word for postpone.
Yeah.
Have you heard that word before? Punt?
Yeah, and in these textbooks, like not normally, but in the textbooks,
Okay. Okay, so multilayer perceptrons. Um,
yeah,
yeah.
multi perceptrons.
Um, in the the chapter, what's it called? Linear neural networks. Okay. In the
It's called multi-layer perceptrons.
no, the
Linear,
previous one.
yeah,
Yeah,
previous one, yeah.
yeah. In the linear neural networks chapter, we introduced softmax regression, implementing the algorithm from scratch and using high-level APIs, and training classifiers to recognize 10 categories of clothing from low-resolution images. Along the way, we learned how to wrangle data, coerce our outputs into a valid probability distribution, apply an appropriate loss function, and minimize it with respect to our model's parameters. Now that we have mastered these mechanics in the context of simple linear models, we can launch our exploration of deep neural networks, the comparatively rich class of models with which this book is primarily concerned. Okay, please go on.
Hidden layers. We have described the affine transformation in the subsection linear model, which is a linear transformation added by a bias. To begin, recall the model architecture corresponding to our softmax regression example illustrated in the figure softmax regression. This model mapped our inputs directly to our outputs via a single affine transformation followed by a softmax operation. If our labels truly were related to our input data by an affine transformation, then this approach would be sufficient. But linearity in affine transformation is a strong assumption.
Um,
Linear models may go wrong.
Wait, what does affine mean?
Uh, it's single transformation, right?
Yeah, can you look it up like in a dictionary or something? Like just the word, no, just affine,
Um,
like just the word affine. Mm.
allowing preserving parallel relationship. So is a linear mapping method that preserve points, straight lines, and planes. Set of parallel lines remain parallel after an affine transformation. So I think it is that that line from one neuron to another neuron. There is a parallel network that is going on, right?
Okay.
Like from one feature to the other feature. Not to the other feature, from one for one feature one weight matrix is applied, that
Okay.
wx, that is actually a linear transformation, and it's also affine. It's like wx1 wx2, so they are parallel transformations.
Okay. Okay. Yeah. Okay.
Yeah. um, you'll read.
Yeah. Okay. Linear models may go wrong. For example, linearity implies the weaker assumption of monotonicity, that an increase in our feature must either always cause an increase in our model's output, if the corresponding weight is positive, or always cause a decrease in our model's output, if the corresponding weight is negative. Sometimes that makes sense. For example, if we were trying to predict whether an individual will repay a loan, we might reasonably imagine that holding all else equal, an applicant with a higher income would always be more likely to repay than one with a lower income. While monotonic, this relationship likely is not linearly associated with the probability of repayment. An increase in income from 0 to 50,000 likely corresponds to a bigger increase in likelihood of repayment than an increase from 1 million to 1.05 million. One way to handle this might be to pre-process our data such that linearity becomes more plausible, say by using the logarithm of income as our feature. Uh, Note that we can easily come up with examples that violate monotonicity. Please go ahead.
You understood, right? Monotonicity
Mm.
means that same relationship. When feature increases, output also increases. It's the
Yeah.
direction is the same. So what they say here is, if we take a feature like salary or income, then with increase in salary, it will be, the probability will be more that the person will repay the loan. But if it is a salary increases just from 0 to 50,000, and loan repayment will be from 1.1 million to 1.05 million, means that may not be a linear relationship. Like there is no strong what do you say, we cannot be sure that that person will repay that 1.05 million.
Mm-hmm. Yeah.
So for that case we are using logarithm.
We. Uh,
One way to handle this might be to pre-process our data such that linearity become more plausible. So by using logarithm of income. So when we use logarithm, the weightage of that feature income will decrease.
yeah. Yeah.
Okay.
Okay.
Note that we can easily come up with examples that violate monotonicity. Yeah. Say, for example, that we want to predict probabilities of death based on body temperature. For individuals with a body temperature above 37 degrees Celsius or 98.6 degree Fahrenheit, higher temperature indicate greater risk. However, For individuals with body temperature below 37 degrees Celsius, higher temperature indicate lower risk. In this case too, we might resolve the problem with some clever pre-processing. Namely, we must use the distance from 37 degrees Celsius as our feature. But what about classifying images of cats and dogs? Can you continue?
Yeah, wait, yes, please. Um, oh, okay, so because okay, so there is no linearity. Okay, I get this with
Temperature.
so that's why we need to use the distance from, okay, so
Yes.
then it will be a linearity. Yeah. But what about classifying images of cats and dogs? Should increasing the intensity of the pixel at location 1317 always increase or always decrease the likelihood that the image depicts a dog? Reliance on a linear model corresponds to the implicit assumption that the only requirement for differentiating cats versus dogs is to assess the brightness of individual pixels. This approach is doomed to fail in a world where inverting an image preserves the category. Wait,
Oh, sorry.
what? What are you doing?
It just slips. I'm not
No,
able to find the scroll
no,
bar, so I
can you go a bit up more? So
yeah,
you
one
can
minute.
also use the arrow keys, right? You know that?
Uh, but
Does it work?
it went till
Uh,
the top. It's okay.
okay. Maybe you should install Windows. I don't know if Windows is better.
Um, yeah.
Uh, so, okay, what about classifying images? I'm still processing that paragraph. Should increasing the intensity of the pixel at location 13 always increase? Reliance on only where wait, we're inverting an image. Oh, so like inverting the color.
Inverting, not not like RGB to BGR, the inversion we did, no? The rotations
Oh,
and
also
other
okay.
things. Yeah.
But I think also the inversion of brightness would also make the linearity fail, right?
Yes, yes, correct.
So it would both. Okay.
Yeah.
Uh,
Yeah,
uh,
in this
um,
case they are referring to brightness itself, because
uh,
initially they talked about intensity of pixel location.
okay. So this would mean the dog would always have to be at the same place, for example. Yeah. Okay. And yet, despite the apparent absurdity of linearity here, as compared with our previous examples, it is less obvious that we could address the problem with a simple pre-processing fix. That is because the significance of any pixel depends in complex ways on its context, the values of the surrounding pixels. Um, okay. While there might exist a representation of our data that would take into account the relevant interactions among our features, on top of which a linear model would be suitable, we simply do not know how to calculate it by hand. With deep neural networks, we use observational data to jointly learn both the representation via hidden layers and a linear predictor that acts upon that representation.
I think
Okay.
I'll read the paragraph again. I did not understand.
Yeah, please.
And yet, despite the apparent absurdity of linearity here as compared with our previous example, it is less obvious that we could address the problem with a simple pre-processing fix. This is because the significance of any pixel depends in complex way on its context, that is the values of surrounding pixels. While there might exist a representation of our data that would take into account the relevant interactions among our features, on top of which a linear model would be suitable, we simply do not know how to calculate it by hand. With deep neural networks, we use observational data to jointly learn both a representation via hidden layers and a linear predictor that acts upon that representation. Okay, like do they say hidden layers are used to understand the surrounding pixels, something like that? And the linear prediction is by the um,
yeah, I'd say like not directly, but like um, the same concept, right? Like um, yeah. Mm,
okay, maybe in the next paragraph it will be clearer.
like they don't explain it explicitly, right? Like it's a bit vague. Like yeah, we should go on. Maybe they explain it in more detail.
Yeah, you can read.
Yes, incorporating hidden layers. We can overcome these limitations of linear models and handle a more general class of functions by incorporating one or more hidden layers. The easiest way to do this is to stack many fully connected layers on top of each other. Each layer feeds into the layer above it until we generate outputs. We can think of the first L-1 layers as our representation and the final layer as our linear predictor. This architecture is commonly called a multilayer perceptron, often abbreviated as MLP. Below we depict an MLP diagrammatically. Okay, so there's an output layer, there's an input layer, there's a hidden layer,
All are connected.
and they use the O letter for the output layer nodes, H for the hidden layer, and X for the input layer. Okay, and it's a dense layer or a fully connected layer or yeah.
Yeah.
Mm,
This MLP
we,
has 4 inputs, 3 outputs, and its hidden layer contains 5 hidden units. Since the input layer does not involve any calculation, producing outputs with this network requires implementing the computation for both the hidden and the output layers. Thus, the number of layers in this MLP is 2. Note that these layers are both fully connected. Every input influences every neuron in the hidden layer, and each of these in turn influences every neuron in the output layer. You can read.
okay, so this is gonna be fun. From linear to nonlinear, as before by the matrix X element of the uh, real
Read.
numbers n by d, we denote a mini batch of n examples where each example has d inputs features. For a one hidden layer MLP, whose hidden layer has h hidden units, denoted by h also element of the real numbers n by h. The outputs of the hidden layer. Here, h is also known as a hidden layer variable or a hidden variable. Since the hidden um, and output layers are both fully connected, we have a hidden layer weights, W index 1, element of the real number space D by H, and biases B index 1, element of the real number space 1 by h, and output layer weights w index 2, element of the real number space h by q, and biases b index 2, element of the real number space 1 by q. Formally, we calculate the outputs x element of real number space x by q of the one hidden layer MLP as follows.
Q is
Uh,
the output.
sorry?
Q is the number of output layers, right?
Oh, the q in the dimensionality, sorry.
Yeah, it's the output layer because um, R D comma cross H, because H is the number of hidden layers.
Yeah, wait.
And that is for W1. If you go back
Okay.
here, this is for W1. There are
Uh,
H layers, so there will be H weights.
so q would be 3 in this case, or?
Yeah, Q would be 3 in this case.
And h would be
5.
5. Okay. There was something at the beginning. So the x is the
X is
is
the
it
input.
is it
4.
x is a mini batch, right?
Yeah, here actually D is 4 and
Hmm.
N is like we N is the size of mini batch.
Hmm. Okay, so n. Oh, okay.
D is 4. 4 input features.
So okay, so yeah, okay. So the but where's the output layer?
This one?
No, in the description, in the mathematical description.
Yeah, they haven't mentioned what is Q, but from the
Oh, you mean I mean the O. They haven't defined the output layer O.
yeah, they have defined it as in the equation coming next.
No, but they haven't given the dimensionality.
Yeah, they
Like
have,
they
but it
okay, it's
is assumed as Q because Q
mm,
comes out of nowhere, and W2 will be for output layer weight. They have mentioned like W2 is for output layer weight. Then H by Q means there are H by Q.
okay.
This is N, D by H,
Okay.
first layer. That is D by H here, this one.
Okay.
Okay.
So um, can you go on?
Yeah. Um, Formally, we calculate the outputs X element of R
Okay.
n by Q here.
Yeah. Okay.
Calculate X element of R n by Q of the one hidden layer MLP as follows. H is equal to X into X dot W1 plus B1 and O equal to H dot W2 plus B2. Yeah, B2 is 1 by Q and B1 is 1 by H. That's clear, right?
Yeah.
Note after that, after adding the hidden layer, our model now requires us to track and update additional sets of parameters. So what have we gained in exchange? You might be surprised to find out that in model defined above, we gain nothing for our troubles. The reason is plain. The hidden units above are given by an affine function of the inputs and the outputs, which is pre-softmax. This output is not output of softmax, are just a fine function of the hidden units. That is, they are just parallel, simply parallelly multiplication is happening there. Like in this case, we are just multiplying x1 into h1, x1 into h2, like that parallel multiplication is happening. So they are just a affine function of the hidden units. An affine function of an affine function is itself an affine function. That is we multiply x1 into h1, and then we obtain w2 into h1 as o1, then it's like one affine over another affine. It is again an affine function that we receive at O1.
Okay. But is affine, I was thinking it's a linear function, but that's, wait, so they say
This is a linear.
nothing is gained. They say we gain nothing for troubles.
Yeah.
Um,
So this is a linear function, right?
yeah.
So this equation, it is actually being parallelly happening for every feature to every hidden layer. That is why they call it affine. Like this.
But the problem wasn't, is like affine and linear are two different things, right?
No, affine and they are same. It is a linear mapping.
Ah, okay. Ah, okay. Okay. So the same, like remember the example with body temperature, or yeah.
Yeah,
So the
like
same problem, or the one with the pixel in the,
dogs and cats. Yeah.
yeah, the problem would still be the same with this model.
Yes.
Okay. Okay, so that concludes the first 25 minutes. Let's have a break then.
Okay. So we read till here, right?
Yeah.
Yeah.
And the timer. Um, mm, Moreover, our linear model was already capable of representing any affine function. Okay. So it's actually like the multi-layer network we have now is the same as the
Linear.
one layer, as
Yes.
the one layer one.
Yes.
Okay. So there's not any benefit at all.
As of now.
Okay. We can view the equivalence formally by proving that for any values of the weights, we can just collapse out the hidden layer, yielding an equivalent single layer model with parameters W equals to W1 by W2 and bias 1 W2 plus B2. Um, oh, because the second bias is influenced by the hidden layer. Is that correct?
Uh, yeah, correct. So instead of W, instead of like B1 plus B2, it's actually B is a combination of
Okay.
B1 W2. No, no. Um,
Okay,
the
so
weight is W1 into W2. Oh, if you see here, this is W1. No, this is W1 and this is W2.
yeah,
So what we receive here will be W1 into W2.
yeah.
And for bias, it should be B1 plus B2, but they have represented it as B1 W2 plus B2.
Mm.
Um, okay, I think because the final bias will have an effect of the hidden layer.
Okay.
Once again, we can view the equivalence formally by proving that for any values of the weights we can just collapse out the hidden layer, yield an equivalent single layer model.
Okay.
Okay, they are trying to represent it as one model, and then this will
So
be the equation.
yeah.
Yeah.
So now we see that this is actually the same as the linear
Hmm.
neural network we saw before.
Yeah, W x W plus B
Okay.
without
Uh,
softmax.
without softmax, yeah.
Yes.
Okay, the linear regression.
Yes.
Uh, okay. Uh, in order to realize the potential of multi-layer architectures, we need one more key ingredient, a non-linear activation function. Is it theta or was it that? What
Sigma.
is that?
Sigma.
Huh? Sigma.
Sigma.
Sigma to be applied to each hidden unit following the affine transformation. In general, with activation functions in place, it is no longer possible to collapse our MLP into a linear model. So if H is sigma of linear regression, and then O is H by W index 2 plus B index 2, we can't collapse it anymore since each row, can you go ahead with reading? Since
Yeah.
each row,
You understood, right? The sentence?
yeah. Well, yeah. Not deeply, but like shallowly.
Yeah.
Let's just continue reading.
Okay.
Um,
Since each row in X corresponds to an example in the mini batch with some abuse of notation, we define the nonlinearity sigma to apply to its inputs in a row-wise fashion, that is, one example at a time. Note that we use the notation for softmax in the same way to denote a row-wise operation. Reference subsection softmax vectorization. Yeah, we were applying softmax to every rows. Remember?
mm, mm,
Similarly, we are applying the sigma also to every element in the row.
mhm.
Often, as in this section, the activation function that we apply to hidden layers are not merely row-wise but element-wise. That means after computing the linear portion of the layer, we calculate each activation results without looking at the values taken by the other hidden units. This is true for most activation function.
Oh, okay. So row-wise versus element-wise means the softmax needs the output of the other nodes, right?
Yes,
Too, and often the activation function will just be it will work without the outputs from other nodes. It will work just on one
one node.
node output. Yeah.
Yes.
Okay. Okay.
Build more general multi-layer perceptrons, we can continue stacking such hidden layers. Example, H1 equal to sigma 1 of x into W1 plus B1, and H2 is sigma 2 of H1 into W2 plus B2. So it will be like H1 is the first layer, then on top of it, sigma will be applied to this result like that.
Okay.
But with each layer, we add new bias.
Mhm.
Universal approximators. Oh, sorry. On top, yielding more expensive models.
Expressive.
Sorry, expressive models. Can you continue?
Expensive models is like, I don't know, Heidi Klum or is an expensive model. Universal approximators. MLPs can capture complex interactions among our inputs via their hidden neurons, which depend on the value of each of the inputs. We can easily design hidden nodes to perform arbitrary computation, for instance, basic logic operations on a pair of inputs. Moreover, for certain choices of the activation function, it is widely known that MLPs are universal approximators. Even with a single hidden layer network, given enough nodes, possibly absurdly many, and the right set of weights, we can model any function, though actually learning that function is the hard part. Can you reread that sentence? I didn't really understand it. The paragraph, can you start from the
Multi
headline? Yeah.
Universal approximators. Multi-layer perceptrons can capture complex interactions among our inputs via their hidden neurons, which depend on the values of each of the input. We can easily design hidden nodes to perform arbitrary computation, for instance, basic logic operations on a pair of inputs. Moreover, for certain choices of the activation function, it is widely known that MLPs are universal approximators. Even with a single hidden layer network, given enough nodes, possibly absurdly many, and the right set of weights, we can model any function, though actually learning that function is the hard part. So what
Okay,
we
wait,
see,
so, sorry.
no,
Yeah.
you can.
So we could model any function. What could be like
They are talking about,
exciting examples for this, like any function? Could it be like could this function be driving a car, for example?
yes, you remember Mandela told us with one layer of,
Okay,
no,
but
with
he
one,
said one layer, or was he referring to one hidden layer?
no, he referred to one node. He said he used only one node. Oh,
One
oh.
node?
Yeah, yeah, I specifically
One
remember.
output node. One output node. Yeah, yeah, but
Oh,
yeah, this one is correct.
yeah,
One output node, yeah.
yeah. So what it explains here is, um, like even with one layer, we can have any function to be applied. So here, sigma, they use sigma here, right?
No, I'm just interested in what could be examples for they say we could model any function, right?
Um, yeah, it could be like object detection.
Okay, so like how difficult could the task be? Like could it be like I don't
Yeah,
know, writing, could it be a function that takes the input of I don't know, Wikipedia and a prompt to write a scientific paper and then outputs a scientific paper for archive, for example? Could that be a function?
yes, but provided that it should be a supervised learning. For
Yeah.
example, like
No,
it
no,
should
no,
have,
no, regardless of the learning, just like extremely theoretically, because they say possibly absurdly many nodes, right?
yeah. So if there
And then
are,
the right set of weights. So that is given. The right set of weights is given already. So we don't have to bother about learning. Just like what would be possible?
yes, that example can be possible because if you see what is it, VGG network and all, they are examples of such kind of, um, like even with their one layer, they
Mhm.
perform very good at like drawing
But
images.
when you say one layer, you mean one hidden layer, right?
One hidden layer, yes, one
Yeah,
hidden layer.
please state explicitly because like yeah, yeah, okay.
Okay. Yeah, well,
All
so
right.
with one hidden layer and many nodes,
Like absurdly many nodes.
absurdly
Like
many nodes, you can actually write with given words, we can give a context and write a poem, a story. That is a possible application. Like you said,
mhm,
writing scientific paper, or even analyzing pictures for not pictures, location,
mhm.
like where
But But why are we using more layers than one then?
Here, that is what actually the learning function is the hard part.
Okay.
So why do we learn? We learn to provide the right set of weights. This one hidden layer node will work perfectly only if we have the right set of weights.
Mm.
So in order to find that right set of weights, we need more hidden layers.
Mm-hmm. Okay.
Because
Um,
in one hidden layer, one set of learning will happen. In the second hidden layer, second set of learning will happen, and then the back propagation will happen. So again, an update of weights will happen, and finally the trained model will give us a right set of weights, which can be
okay.
applied on the test data set.
Okay. Um, you might. Uh, who was reading, by the way?
I was reading.
Okay.
No, did you
Oh
get
yeah,
the?
yeah, you were rereading it. Yeah, yeah. It's good that we reread it. Like, um, you might think of your neural network as being a bit like the C programming language. The language, like any other modern language, is capable of expressing any computable program, but actually coming up with a program that meets your specifications is the hard part. Okay. Moreover, just because a single hidden layer network can learn any function does not mean that you should try to solve all your problems with a single hidden layer networks. In fact, we can approximate many functions much more compactly by using deeper versus wider networks. We will touch upon more rigorous arguments in subsequent chapters. Okay.
So they are plotting. Did I run the cell before that? Okay. How do you run it all? Like run from?
The first one, yeah. First one.
No, you run from that line to the next, right?
Um,
We will see it later. Yeah, okay. Activation functions.
yeah, you were asking for another, not for the run R, right?
No, no. Oh, run after. Yeah, that one.
Run after, okay.
Yeah, activation functions. Activation functions decide whether a neuron should be activated or not by calculating the weighted sum and further adding bias with it. They are differentiable operators to transform input signals to outputs, while most of them add non-linearity. Because activation functions are fundamental to deep learning, let us briefly survey some common activation functions. Okay, so um, when you take linear models, right, actually only an affine transformation is happening there, Wx plus b. But if you want more learning to happen, we are using activation functions. These activation functions can be any other mathematical functions that will be applied on the inputs, which will help us in better learning.
But if it depends on the function, right? If it's just another linear function, then it will not change anything.
Yes. So if sigma of Wx plus b is another
Fine.
then it will be again affine. It will not change.
Yeah.
So
Okay.
now we are going to study more functions that are not affine. First is the Rayleigh function. The most popular choice, due to both simplicity of implementation and its good performance on a variety of predictive tasks, is the rectified linear unit. ReLU provides a very simple nonlinear transformation. Given an element x, the function is defined as the maximum of that element and 0. So ReLU of x equal to maximum of x and 0. Informally, ReLU function retains only positive elements and discards all negative elements by setting the corresponding activations to 0. To gain some intuition, we can plot the function. As you can see, the activation function is piecewise linear. Okay.
Okay, yeah.
So here, if you see, we have only two values. Uh, to as in is it is either 0 or anything greater than 0.
Yeah.
So if
Okay.
like 0 4 means 4 will be the answer. So at this point the answer will always be 2. At this
Yeah.
point answer will always be 1, like that.
Okay. So it's basically dropping negative numbers.
Yes.
When the input is negative, the derivative of the ReLU function is 0, and when the input is positive, the derivative of the ReLU function is 1.
One
Note
minute.
that the,
1 minute. Can you verify that from this graph? If it is negative, the
yeah, wait.
derivative will be 0, because the tangent.
Can't I use annotations? Oh, yeah, here. So let me check. So okay, so here it would be like this. Um, I'm not sure how to paint it here, but
Here you don't have the y changing, right?
yeah,
Usually the hypotenuse, it will be a y by x, right? Delta
yeah,
y by delta x. Here the delta y is 0.
yeah.
So our
Uh,
derivative will be 0.
so it's like a constant function, basically.
Yes, it's a constant function. It's always 0. It's not changing in negative.
Okay.
Yeah.
Note that the reluctant, it's an abbreviation for reluctant.
No, ReLU,
Yeah.
rectified linear unit function.
Oh, okay. I thought it was for reluctant.
No, rectified linear unit. Rectified means because negatives are rectified to 0.
Okay, but it's funny because reluctant would also it would
Yeah,
also be true,
yeah,
right?
yeah, it gives a sensible meaning.
Yeah, but it's a relo. Okay. Um, Note that the relo function is not differentiable when the input takes value precisely equal to 0. Wait, there is someone at the door. Okay, so let's continue.
Note.
Note, yeah, when the input takes equal to 0.
Yeah, even in
Ah,
this,
okay.
no derivative.
Yeah. Okay, at 0, it doesn't have a derivative, or
No, because even at 0, delta y is 0, right?
no? But they say like note that the Radial function is not differentiable when the input takes value precisely equal to 0. In these cases, we default to the left-hand side derivative and say that the derivative is 0 when the input is 0.
Because delta x is also 0, and it will become like by infinity. No, infinity, right? Division by 0 is not possible in this particular point.
Yeah.
Delta y is 0, delta x is also 0.
Okay. We can get away with this because the input may never actually be 0. Okay, there is an old adage. What, do you know how to pronounce that one? Adage? Adage. Adage.
Short statement. Okay.
Adage.
Adage.
Adage. It's proverb or short, like a saying, like an old saying. You know, there's also an old adage that scientists always use words that seem elitist.
Scientists always use words.
Words that nobody understands. For the
Yeah,
for
so that it looks very complicated. And
I didn't. You said that. I didn't say that. Okay, so we have another 5-minute break.
okay.